in Excel physics, you guys don't go into this at all, but if you're interested in physics, kind of at a more deeper, like at a more deep level, if you're a more intrepid Excel student, quantum mechanics is like the coolest physics thing ever. It's mind-blowing, it's mind-boggling. And you don't like go into this even in AP. It's not like practical knowledge for any of your high school career. But if you're interested, then definitely watch this video, because I'm going to teach you a little bit about the basics of what goes on at the more fundamental level, like of particles and stuff. And it's basic math, it's still tough, and probably you need to do a little bit of calculus in order to really understand what's going on, but it doesn't go nearly as deep as quantum mechanics can go. It's not hard at all compared to that. But if you do want to dip your toe into the water that's all of that quantum mechanical and all that relativistic stuff that is like the more deep theory of physics, then definitely watch this video because it's super exciting. Also, it occurs to me that this video is in portrait mode, so if you're watching this like on a computer, then sorry, but you know, whatever. If you're watching it on a phone, that's good, and it's more portable, so if you're like on the train or texting and driving and watching this, then yeah, definitely, it's good. Okay, anyway, it occurred to me again that I set up my thing, like my camera, in this weird like cookie rack thing, and it's gonna be in it's gonna be landscape mode now, so again, sorry again. It's gonna switch around. Maybe I'll put like a cool border around it. I probably won't. It's just gonna be black probably. But anyway, enjoy. And if you're texting and driving, don't look at the screen, but listen. Yeah. Okay, so in classical mechanics, we might have a particle with a certain mass. We can determine its qualities based on forces, which give us our velocity and our position. And all of these things are concrete. So like, I'm in my bedroom right now, and there's lots of books in my bedroom. If I took one of these books and I threw it out my bedroom window, then if we're looking at the motion of the book in one dimension, just up and down, I know that there's a single force, primarily gravity, you know, acting on the book. And using this force, which is known to me, I can figure out its position and its velocity and its acceleration at a certain time t after I've thrown the book. All of these numbers are concrete values. Like, we know what they are. They're specific numbers. But in quantum mechanics, we don't have these concrete things. And in place of F equals ma in Newton's second law, we have a wave function to consider the more physical properties. We arrive at this wave function using Schrodinger's equation, which is right here. Okay, so Schrodinger's equation is I, which is radical -1, the imaginary number, times h, which is a constant that I'll describe to you later, times the derivative of the wave function with respect to time, and that's equal to the negative constant squared, over 2 times the mass of the particle that we're studying, times the second derivative of the wave function, but this time with respect to position and not time like here. And you just add that to the velocity of the particle in question times the wave function again. So I'll just go through all the variables and explain them to you. Again, I is just the radical of -1. H is Planck's original constant, but it's divided by 2 pi, which doesn't really mean anything to us, but specifically what we can use is 1.054573 times 10 to the -34th joules times second. Mass, again, m, mass, is the mass of the particle that we're studying, and this symbol right here is the symbol for the wave function. It comes up here, here, and here. Now, Schrodinger's equation is primarily used so that we can figure out what the wave function is, so we're kind of trying to solve for it. And v is the velocity of the particle. So the wave function is the quantum mechanical representation of Newton's second law, F equals ma, but it does not tell us position as in classical mechanics. We receive no concrete information from the wave function. What we receive is a probability distribution. So this distribution is given to us by Born's statistical interpretation of Schrodinger's equation of the wave function. So let's, okay. Is that good? That's probably fine, right? No. Okay, cool. So this is where quantum mechanics becomes pretty fascinating and kind of incomprehensible. You see, we can't know where elementary particles are, only where they might be. The universe is fundamentally indeterminate. So in this graph, we see the manifestation of Born's statistical interpretation. So here we have the wave function's absolute value squared. And here we have x on this axis. So, let's see. So A at this position A, we see that the probability is high. It's likely that we'll find the particle here, the particle that we're studying. At B, this is supposed to be touching the x-axis. At B, it's impossible to find the particle because the probability is 0. So that's maybe a little bit, you know. And then at C, it's just less likely than at A. So the shaded area, right here, dx times the wave function, this shaded region, the area of that, gives us the probability of finding the particle in this region. So there are 3 positions which we might take here. Suppose we measure the situation and we figure out that the particle is actually at point C. So here are the 3 interpretations. First, we have the realistic interpretation. So we measured the particle and we found that it's at point C. The realists say that this could mean that the particle was at point C. Not that it is there, but that it was there when we measured it. But this is kind of like a flawed interpretation, because we will have learned little about the particle. The predictive theory, which the wave function represents, does not actually tell us anything, and so it's incomplete by this position. And this is the position that Einstein stood by. The second position is pretty crazy. It's the orthodox position. And the people believe that the particle was not really anywhere prior to the act of measurement. As per this mindset, the particle only assumes a definite position in space when it's measured. The act of measurement is what forces the particle into taking a stand and taking a real physical position. So when I look around my room again, I have the books and the lamps, and all of these kind of determinate fixtures. I can see them and I know where they are. Their qualities, their physical properties are certain to me. But according to quantum mechanics, those qualities, if we're looking at the fundamental level, like the more elementary particle level, these qualities are uncertain. In fact, they don't exist until I perform my human act of observation. And this act of observation forces the physical world into brief certainty. And this is crazy. Einstein said God does not play dice, but according to the orthodox theory, which has been proven, as I will go into, God does play dice, if you believe in that, you know. Anyway, the third interpretation is the agnostic position, although it has, for the most part, lost its merit. This position claims that the argument about certainty is somewhat useless, per its proponents, and I quote right now, "What sense can there be in making assertions about the status of a particle before a measurement when the only way of knowing whether you were right is precisely to conduct a measurement, in which case what you get no longer is before the measurement?" That's end quote, by the way. So the details of this experiment that I'm about to describe to you will not be detailed here, but in 1964, John Bell confirmed the agnostic position through experimentation. You see, before measurement, a particle lacks a particular position. It is the act of measurement which impresses upon the particle a position and this quality. After measurement, the wave function collapses, assuming one position only. So if we say, we measured the particle and we found that it's point C, if we go back and we measure it again, the wave function does no longer exist. It's no longer a probability distribution of multiple probabilities. It's just the particle will only ever exist at point C if you've measured it and you found it to be there. So if we give merit to the simulation theories, which say that the universe is a simulation in some hyper advanced civilization, then the quantum indeterminism here would be pretty sensible. Instead of assigning to every component of the simulated universe a definite position, just allow the components to shift into definite positions and to shift into existence when perceived or measured. It's easier on whatever is processing the simulation to allow the particles to exist as probabilities which trick the observing eye to believing in their determinism only when observed. But in the quantum theory, we have discovered something of a slip, which contradicts our traditional view of the world. It is a quantum mechanical world, not a classical one, and we still have much to learn. But anyway, that's all. It's not a lot of content, but I think it's pretty cool, and hopefully you enjoyed it too. But thank you for watching.